In the last section, we talk about the proof of the Cauchy-Riemann equation and also the application of the Cauchy-Riemann equations, which can be applied to analyze whether a function is analytic or not. And in this section, let us have some concrete example of analytical functions. The first example is the power function. Means that W equal to F, Z equal to Z power N, okay, nth power. We can expand this function in this way and then find out the real part and the imaginary part. And then we can check that U and V satisfy this set of Cauchy-Riemann equations. So we know that this function, the power function, is analytic in the entire plane. In fact, all the examples shown in this section are analytic functions. Okay, so you can see there are a lot. Yeah, you will see. The next example is the polynomial. We have W equal to Fz, and then C0 plus C1z plus C2z square, and so on and so forth. And note that C0, C1, C2 here are constants. They are real number or complex number. Both can be, which is just a very straightforward generalization of the power function. We just add many terms of power function all together to create a polynomial. Okay, this function is also analytic too. One more a little bit complicated function is the fractional function. Means that this function is constructed by two polynomials. Okay, here Pz and Qz are polynomials. Okay, and then P divided by Q. We call this the fractional function. This function is also analytic. Okay, one more function is the nth root. Here, W equal to Fz equal to nth root of z. Okay, according to the polar form of z, we can write our function in this way. Okay, and because cosine and sine are periodical function with the period 2k pi, we can add a 2k pi term here divided by n, and also k1 from 0, 1, 2, 3. This can be proved to be equivalent to this one. Okay, and also we take k equals 0, and then obtain the principal value. See, we have infinitely many values of W here, and for convenience, we say we take the term principal value to give it for the function in the case k equals 0. Okay, and also we have one more function called the exponential function. Here W equal Fz equal to exponential z, or in some textbook you can find that it will be written in a capital E, exp, and bracket z. Okay, and then we can try to manipulate this function by putting z as x plus iy, and then we can use the Euler formula to decompose the exponential iy into the real part and imaginary part, and then we can also write this term as this term. It is the absolute value of the z exponential z because we have this relation. In this way, we can decompose this function into the real part and the imaginary part, okay, u and v here. We can check that the Cauchy-Riemann equations are satisfied, okay, easily. You can do it by yourself. One more function is the trigonometry function. The most famous one is the cosine psi function. We have the definition that cosine z equal to 1/2 of exponential iz plus exponential minus iz, and then psi z equal to 1 over 2i times exponential iz minus exponential minus iz. You may doubt that in this way, do we still have the famous property of the same same famous property? See, for the real trigonometric functions, we have some famous property. We will doubt that whether we still have such kind of famous property here. The answer is yes. Actually, we have cosine z squared plus sine z squared equal 1. Here, z equal to x plus iy, remember. Okay, and also we have the cosine z1 plus minus z2 equal to cosine z1 cosine z2 minus plus sine z1 sine z2 here. And also we have the differentiation, the same, just like those in the real case. And also we have the Euler formula to relate the exponential function to the sine cosine function. And also we have the period 2n pi here. Actually, many of the famous property for the real sine cosine functions still apply to the complex sine cosine function. Okay, one more type of functions is the hyperbolic functions. We define the hyperbolic cosine and hyperbolic sine function by this formula. Okay, and we find it is easy to find that hyperbolic sine just equal to cosine iz. Hyperbolic hyperbolic z equal to cosine iz. Hyperbolic sine z equal to minus I sine iz. And also we have some relations between cosine function and hyperbolic function. See, cosine z here can be written as cosine x plus iy, and then we expand it in this way, and then we say that cosine iy is just hyperbolic cosine y, and then cosine sine iy is just I hyperbolic sine y. The reason why we have this equality is written here. If you have trouble to understand this part, you can ask me in the class.